In this Mind Bite, we look at electromagnetic waves. First, we do some revision on the 1D wave equation and its solutions. Next, I extend that to more than one dimension, so n dimensions. And finally, we look at electromagnetic waves as solutions to the n-dimensional wave equation. So you would have encountered the one-dimensional wave equation as given here. You can think of this as just Newton's law. Force equals mass times acceleration. The derivative on the right-hand side is just an expression for acceleration. It's the rate of change of velocity, so it's the second derivative of position. The left-hand side describes the force, because we're talking about a disturbance travelling, for example, along an elastic string. The return force of a piece of elastic doesn't depend upon what height it is. It doesn't know what its absolute height is. It doesn't matter if the elastic is held on a slope or not. What matters is the curvature, because the two sides are pulling with a component in the same direction. And so you get a resultant force on each little element, which depends upon the curvature. And the curvature is given by this second derivative on the left-hand side. So this is force equals this constant times acceleration, where the constant is a mixture of the mass and the inertial part due to the acceleration, and from the Hooke's law, force as a function of curvature. So this constant has both those properties built into it. However, it can be interpreted as 1 over the phase velocity. So c here is the phase velocity. As an example, we show that the classic cos curve can be a special solution of this differential equation. And we have an expression of a travelling cos wave here. The omega is the angular velocity. So it tells us what happens if we look at one point. How does this value go up and down? How fast does it go up and down? Well, it goes up and down with some phase velocity described by omega, which is 2 pi times the frequency of it going up and down. Because this number inside the brackets has to be an angle, because cos can only work on an angle, omega converts a time into an angle, so it has units of angle per unit time, angular velocity. The k is very similar. It turns a displacement into an angle, so it is radians per unit distance. The k is the wave number, and you can think of the wave number being like taking a photograph of this cos curve. So time is a constant, and you could treat it as time 0. You see, if this term is 0, you just get a cos curve. K describes how far you have to go in the x direction to go through one period. Each time you go through the wavelength lambda, then kx changes by a factor of 2 pi, and so our cosine goes through one period. Now this is a solution of the 1D wave equation. And to show it is, we need to put this into the wave equation and show that the left-hand side equals the right-hand side. So the left-hand side means differentiating this with respect to x twice. The first time you do it, the cos turns into a minus sign, and you get a factor of minus k coming outside. The second time you do it, the minus sign turns into a minus cos, and you get another factor of minus k coming out. So you're left with a term which is minus k squared times our original cos curve. Similarly for the right hand side, if you differentiate this thing with respect to time, then the cos turns into a minus sign and then back to a minus cos. And each time you differentiate, an omega comes outside, so you're left with minus omega squared times our deformation. The 1 upon c squared comes from the 1 upon c squared up here. Now if these two things are going to be equal to each other, that tells us that c is plus or minus omega upon k. The plus or minus comes from doing the square root of everything. You see, if we rearrange this, we get c squared is omega squared over k squared. So we don't know about the sign, which means that k can be thought of as plus or minus, and that determines whether the wave is propagating to the left or propagating to the right. You can always remember these around the right way, because you know that c is a phase velocity, so it is a distance per unit time, where omega has units radians per unit time, k has units of radians per unit distance. when you do this division, you get distance per unit time. This expression can also be derived from considering the term inside the brackets here. The phase velocity is how fast a point of constant phase travels. A point of constant phase could be a maximum or a minimum or a zero crossing. Consider the case where our phase is equal to 0, i.e. omega t minus kx are equal to 0. If we increase time a little bit and we increase x a little bit, then we'll move to some different point in phase. But for special ratios of time at t and distance x, the phase will remain as 0. Now, if you increase t by a bit and then increase x by just the right amount, then the amount that omega t increases is cancelled by the amount that kx increases, and you stay at a point of constant phase. That ratio of how much x changes to how much t changes to keep this term equal to 0 is our phase velocity, because it's how fast a point of constant phase moves, and it is omega upon k. In more than one dimension, we have to take into account the bending in the other directions. So in one dimension, we only had one dimension we could bend in the x direction. But if we have an x direction and a perpendicular y direction, or possibly an x1 and an x2, then we have to take into account the bending in both those directions. And the Laplacian operator does that. The Laplacian of our disturbance is the sum in all these orthogonal directions of the bending, or the second derivative in those directions. That's because if you bend in the x direction, it gives you one component of return force. If you bend in the y direction, it adds to that force. So you add up all the forces due to the bending in the different directions. And so we replace the left-hand side of our one-dimensional wave equation with this Laplacian, and it becomes an n-dimensional wave equation. You can see if n is equal to 1, then it just reduces to the one-dimensional wave equation we had a moment ago. The travelling cos solution looks very similar, except now our cos has to be a cos in x and in y, which means we have to allow for moving in x and moving in y. Now that gives us two wave numbers, the wave number in the x, which is 2 pi divided by how far you have to go in the x direction to go through one entire period, and the same thing for the y. And we can express our displacement term as the dot product of this wave number vector with our position, which is given by this vector xy. Now we can show that this is the solution, and it's very similar to the solution we had before. Now, when we do our derivatives with respect to x1 and x2, or with respect to x and y, then once again our cos goes to minus sine and then back to minus cos. When we differentiate with respect to x, we get a minus kx coming out the first time and another minus kx coming out the second time, which gives us a kx squared. We've got a minus sign from differentiating the cos twice, and so the first term of this summation gives us a minus kx squared. Differentiating with respect to y gives us exactly the same thing, but now it's got this ky squared, and this you recognize as the squared Euclidean norm of the wave number vector here. The right hand side is the same as it was before, and so our phase velocity is now given by omega over the absolute value of k, which is the square root of the Euclidean norm. So it's the square root of this term here, which is just the length of the vector, this vector, the wave number vector kx over ky. Right, so that's our n-dimensional wave equation. Oh, Maxwell knew that. He spent an afternoon just looking at Maxwell's equations, although they weren't called Maxwell's equations at the time, and he noticed that there must be a term missing for them to be consistent. And when he added that term and did some vector manipulations, he produced two expressions, one for an electric field and one for a magnetic field. H is related to the symbol B by this factor of the permeability. Maxwell just wrote down all the electric properties he could think of and labelled them A, B, C, D, E. And he got to H for this magnetic field term here. Now you'll recognise both of these equations are n-dimensional wave equations. So the electric field and the magnetic field can propagate like a wave in a media. You'll also recognise that this term is 1 upon the phase velocity squared. It appears in both these expressions, which means an electric wave and a magnetic wave will propagate at the same speed. Now the manipulations that got us here started off with the magnetic field and the electric field in the same equations. So although they're expressed here as two independent wave equations, they're actually coupled. And so you get an electromagnetic wave, or electromagnetic wave, that propagates at the speed given by 1 over the square root of this term, the product of the permittivity and permeability. And they are mutually coupled. You can't have one without the other. So just how fast is this phase velocity? 1 over the square root of permittivity and permeability. Well, if you bang in the numbers that we've given in the previous notes on the electrical properties of materials, and you stick it in the formula, you end up with 3 times 10 to the power of 8 meters per second, which was just the known value of the speed of light at the time that Maxwell did this. So the work he did here, he showed that light was an electromagnetic wave, and that was a major step forward, because nobody had equated light with electric and magnetic properties at that time. So this is what an electromagnetic wave looks like. It has an electric field and a magnetic field, and they are mutually perpendicular. They're always perpendicular to each other, and they're perpendicular to the direction of propagation. You can see it looks like a fixed cos wave moving along, and so this solution is just that travelling cos wave we described in the 1D wave equation. In this case, it's coupled with a magnetic wave which is perpendicular to it, which propagates at the same time and in phase with it. So this is a particular solution of Maxwell's equations for a travelling electromagnetic wave. The direction that the electric field points in determines the polarization of the wave. And in this case, you can see if the electric field is red, then it's pointing in the x direction. And it's always pointing in the x direction, so it's linearly polarized. It always lies along a line. But it can be circularly polarized, where the electric field rotates in a circle as it propagates along. So we'll talk a lot more about electromagnetic fields next semester when we do transmission lines. But with the 1D and ND wave equation we've derived, and knowing the electromagnetic fields are solutions of those wave equations, we can work out how electromagnetic signals propagate through the sort of transmission line that we're used to, such as waveguides or coaxial cables or even copper wires. And we'll look at more of that next semester. So that's the end of the material for 57010.